One-dimensional kinematics is actually about describing motion. It's sometimes said to be the study of motion. There's also dynamics, which is the study of the causes and the changes in motion. If you put kinematics and dynamics together, you get mechanics, and we are studying classical mechanics. But kinematics is simply describing motion. Some good descriptors of motion would be speed, velocity, acceleration. We also have the jolt, sometimes called the jerk. These are interesting concepts in and of themselves. Acceleration is one of the most important concepts that we will study. Acceleration is a good measure of changes in motion. We'll also be talking about a motion as a change in position relative to a reference frame. Our most common reference frame will be the Earth with synchronized clocks. And it is said that all motion is relative, but relative to what? Well, it's relative to a reference frame. For right now, we're going to use Earth with synchronized clocks. The main reference frame we will be using is known as an inertial reference frame, and we will talk about that in class in detail. The very first physics model you should be familiar with is the speed formula. Speed equals distance over time. Your speedometer in your car actually measures your instantaneous speed, the speed at any particular moment. Now, if you were to use this formula to calculate your speed to travel from school to, say, Cedar Point, if you took the total distance traveled and divided by the time it took you, you would actually be calculating the average speed without any knowledge of the detail of the motion. We will be calculating averages quite a bit in this course. And this is a picture of what's known as a world line. It is a position versus time graph. You could think of it as like a date book. It's your history. It tells you where you were at any particular time. We usually use this to represent the motion of a particle. We'll be treating most objects as a point particle using the particle model. And the reason we do that is because you can treat a mass as if it's concentrated at a single point. It's called the center of mass. Sometimes we refer to it as the center of gravity, but the center of gravity and center of mass are really two different things. They're not necessarily the same point. It depends on if the mass is in a uniform gravitational field. This brings up a question in philosophy. If you know the initial conditions, all the initial conditions of a particle, let's just call it a point particle, could you predict with certainty the future events of that particle, like how fast it will be going at a later time, what's its acceleration going to be, those sorts of things? Some in the past thought that you could do this, that the universe was like a clock, where if you understood how all the gears worked, how they all meshed together, that you could perfectly predict the operation of this clock. And it was known as mechanical determinism. But that has been challenged, especially with modern science and the Heisenberg uncertainty principle and a variety of other things that we'll talk about when we get a chance. And it always brought up a debate between mechanical determinism and free will. And I would like you to think about this question, and we will post some of this in class. It always is brought up in physics, some of these issues with making predictions and the idea of free will. So I wonder what you think about that. So some of the motion concepts. We have position. We label it with X. We think of the X-axis. Sometimes it's called the instantaneous position, but position for short, and we label it X. So it's where an object is relative to some origin. You do have to have a reference point with respect to the origin. We usually assign the origin as 0. This isn't always necessary, but we usually assign it 0. So 0 in this case is a position marker. We also choose this, based on the problem we're doing. It really is arbitrary where we put the origin, but once we establish the origin, then we will attach numbers to these axes and mathematize the problem. In one dimension, positions lie, obviously on a number line. You have a positive direction, you have a negative direction. You can have positive numbers, negative numbers, or 0. We also talk about displacement, which is a change in position. And we use the Greek letter delta, which looks like a triangle, the Greek letter D, delta. Later in calculus, you'll change that to D. It'll be dx. And you'll talk about differentials and derivatives. So change in position. You start somewhere, you end somewhere. And to measure that change along a number line, you're taking a difference or using subtraction. Remember, subtraction means add the opposite. So if you call position 1 x sub 1, position 2 x sub 2, and that would be at position 1 would be at time t sub 1, position 2 would be time t sub 2, and you would get this relationship here. You start at x1, you end at x2. The change in x is the difference between those values. Now this displacement can be a positive number, a negative number, or 0. The sign will tell you the direction, and displacement has direction associated with it. So it's actually known as a vector quantity. If you remember, a vector quantity is magnitude plus direction. Magnitude actually has two parts, a numerical part, a number, and a dimension, like the dimension of length, dimension of mass, dimension of time. So a good example would be 5 meters. If you want to give direction, you could say due north, or you could say plus 5 meters or minus 5 meters, and it would be in a relative to the origin, or relative to which way is the positive direction, which way is the negative direction. You could represent this with an arrow, where the length of the arrow would be the magnitude, and the direction that it points would be that aspect of it, the direction. So distance is a scalar quantity. It can be completely described by a number with a dimension, 5 meters, 6 meters. It's just trying to explain how much ground you cover. It's always a positive number. The direction is irrelevant. This is recorded, in your car by how many miles you put on your car. Like if you go get your oil changed, they'll check your mileage and then add 3,000 to 5,000 miles to that to remind you to come back 3 months or 3,000 miles over the amount that you have on there. So displacement, change in position, or delta x, or change in x in one dimension. The endpoints alone matter. Details of the motion between the endpoints is irrelevant to do this calculation. It can be positive or negative. It is a vector quantity. It has magnitude and direction. You can represent it with an arrow where the length represents the magnitude, and obviously the direction is given by where the little arrowhead is placed. That would be the forward direction. The tail end, which usually just you don't put anything on that end, that is the opposite direction. So here's some facts. The distance traveled is always positive, but the displacement can be negative. So displacement is different from distance. It's similar, but it has its own quirks. The distance is the total length of travel. The displacement is the net change in position. These are good ways to look at it. The displacement is always 0 for a complete circuit. So yes, it can be positive, negative, or 0. You have to be careful when you're talking about the displacement. There can be a lot of distance traveled, but if you start and end on the same point, the same position, your displacement is 0. Now here is a little graph of position versus time. If you look at it on the y-axis, you can see the position in kilometers, and on the x-axis, you see the time in minutes. So the time looks like 50 minutes on here, and you could ask yourself, what is the total displacement? This could represent walking to the store at a steady rate, then stopping for a moment, then walking back at a steady rate, then stopping for a moment, and then continuing back. It could be your home, school, whatever. So the total displacements, if the yellow line represents going 1.2 meter or 1.2 kilometers, and then waiting, and then returning, and then waiting, and continuing on at a steady rate, you'd return to where you started, so your displacement would be 0. Your total distance, you would sum these numbers up. 1.2 traveled one way and 1.2 kilometers traveled the other way. So if we want to figure out speed, we would have to know this distance. and then we divide it by the time, but it doesn't give us the detail of the motion. That graph gave us much more detail of the motion. It showed where you stopped, where you were traveling at a steady rate. Speed is always a positive quantity. It is a scalar. The direction of motion is irrelevant. If you do add direction, then you're talking about velocity. It may vary depending on the time interval, obviously. We could ask all kind of questions about speed. But remember, it is a scalar quantity. It's about magnitude. So the average speed depends upon distance traveled, not displacement. The speed of sound, for example, is 340 meters per second. It does depend on temperature, but we'll be using that number for the most part. It works out to be approximately 1 mile every 5 seconds. If we look at nerve impulses, and there is a lab we want to do to measure our reaction time, the average reaction time for human beings is about 0.2 seconds, 0.2 of a second. The average speed is a weighted average according to how much time you spend traveling at each second. It doesn't give you too much detail, but it's still useful. Speed is still a great concept, and if you do that activity, that graphing activity I asked you to do, it will reveal some other insights you may not be familiar with. So motion concepts continue. We have velocity. Now velocity is displacement per unit time. Because displacement is a vector, it makes velocity a vector. We're going to be talking about average velocity. So we have displacement on top, time on bottom. I'm using the slash notation in the notes here, but that is division. It's displacement divided by time. Time is an interval. You do have an initial time and a final time. Usually we start our stopwatches at 0. So you could just divide this by t, and t would be your final time. All that matters are displacement and the time interval. The details of the motion are irrelevant. This velocity can be a positive or a negative quantity. It also can be 0. There can be no change. If you write the change in velocity, delta v can be positive, negative, or 0. Just like the velocity can be positive, negative, or 0. It may depend on the time interval, and it is a vector quantity. Magnitude plus direction. There's many ways to express direction, and we'll talk about that as we go through the course. Now here's that graph again in yellow. If we just look at the part in yellow, where we travel, let's say 1.2 kilometers, and it would take us 20 minutes to do that. So from 0 to 20, if we were to calculate our speed, we take the total distance and divide by the time taken. Now you need to convert minutes into seconds. And remember, 60 seconds per minute, so multiply by 60. So 6 times 20. And kilometers, remember kilometers is 1,000 or 10 to the third. So you can move this decimal over 3 spots. So you get 1,200 meters and 1,200 seconds. Equal over equal amount, you get 1 meter per second. Now the velocity is also, the magnitude is 1 meter per second. The positive means you're going in the positive x direction if we treat this as the x direction. But on the return trip, it's going to be negative. And guess what it's going to be here where it's flat? Well, let's look at this part. On the way back, notice the speed. It still has the same slope. Position versus time, the slope is the velocity, and this is a negative slope, so you're going to have a negative velocity. And if you work this out, you still get 1 for this interval, 25 minutes to 35 minutes. Do you have to do unit conversion here? So if we look at this trip, moving at a constant rate, 1 meter per second. Here we're at rest, 0. We're not changing our position, even though time is proceeding forward, as it always does in our normal everyday lives. And here is the negative 1 meter per second. But you end up in this position. You travel 1.6 and then, or 1.2 kilometers, and then you come back. So the question is, what is the speed? And it would be average speed. And what would be the displacement? So here's the answer. The distance is 1.8 kilometers. When you add it up, the speed would be that converting to meters again, multiplying by 1,000. and converting the time to seconds. Remember, you have to multiply by 60. You get 0.86 meters per second. That's the speed. Now let's look at the velocity. When you do the velocity, the displacement, it's less than the total distance because you backtracked. You went up and came back. You backtracked, so the displacement is less. It's still positive because you're in the positive x direction. If the origin's here, you're not below this time axis, you're above it. So when you put that number in, you get 0.29 meters per second. So notice the speed and the velocity are not equal in magnitude. And this has to do with the nature of displacement. Distance just keeps adding up the more you move. But displacement depends on your initial position and your final position. It is a vector. It's a directed line segment. It's a directed line segment. So with practice, you can, form both a qualitative and a quantitative movie of the motion in your head by examining these position versus time graphs. These they're called world lines again. The instantaneous speed is always the magnitude of the instantaneous velocity, but the average speed is not always the magnitude of the average velocity, as this example shows. Speeds are always positive because they do not involve direction, but velocities can be negative to indicate their direction. So classical mechanics, we're talking about point particles, the center of mass. We'll draw free body diagrams. Well, you don't have to be an artist in this course. You can represent any object that has mass with a dot, and then we'll analyze the motion of that dot. Distance again, total length traveled. Displacement, change in position, or delta x. The change in x equals x minus x naught, or x sub 0. You could also write that as x2 or x sub 2 minus x sub 1 or x2 minus x1. I like to use just x for the final position and x sub 0 or x naught as the initial position when you start your timer at t equals 0. So delta x equals x minus x naught. The average speed is distance over elapsed time. Average velocity, displacement over elapsed time. You could write v sub av for average. We also like to use a bar. We just write v and put a little line over the top. We call it a bar, and it stands for average velocity. So delta x over delta t, change in x over change in t. Here's the bar. V with a bar over it means average velocity. That's what we're going to calculate. That is the slope of the line between any 2 points on a position versus time graph. If you want the instantaneous velocity, you will have to find the tangent line at that point and find the slope of the tangent line. You can actually do quite a bit with the graphs. You don't need to use calculus or take derivatives. Taking a derivative is really finding the slope of that tangent line. And we'll talk about that later. So here's the average velocity again. It can be positive or negative or 0. That's what this means. Greater than 0, equal to 0, less than 0, positive, negative, or 0. Speed and direction, you can think of it that way. Interpreting the graph of average velocity, this can be a little tricky. So it is the slope. It is the rise over the run. We'll talk about it being the first derivative of position with respect to time. But to figure that out graphically, you'll find the slope of the tangent line at a particular point at a particular time. Here's a graph of position versus time. It's a straight line, so the slope stays constant. You could form a little right triangle there. There's a 90-degree angle here. This is angle alpha, using the Greek alphabet. You have the change in position here, change in time here. It's just slope. Remember, this is the y-axis, change in the y-axis, change in the x-axis here. These are actual physical quantities now, so we relabeled them, but it's still just finding the slope like you would find in your math classes. So position versus time graph, the average velocity is the slope of the line between any 2 points on the graph. Alpha is positive in this case, it's a positive slope, so it have a positive velocity, and it's a constant slope, so it has a constant velocity. If you look at the angle alpha, you can tell what the sign of theta is. It's a positive angle. Remember, angles that go counterclockwise are positive and clockwise are negative, where this would be your terminal side. Now here is a way to conceptualize going from average to instantaneous. If you look at the motion graph here, which is this purple line, and I want to figure out the average velocity between T1 and T2, I would just draw a line between those points and I'd figure out the slope of that line. But I'm missing some of the details of the motion. However, I could get more details of the motion if I move these points closer together. I make this time interval smaller. And that's what I'm going to do. If you zoom up on it and I bring these, I make this time interval smaller, this line starts to just kiss this curve. And if I get it to just kiss the curve right at this point here, that would become the tangent line. If I backtrack on this, these are known as secant lines. I can keep creating all these lines are known as secant lines, but once I finally get right on that point, I would draw a line that just kisses this curve. I don't have the line drawn in here, but it just kisses the curve. And if I figure out the slope of that line, it's known as the instantaneous velocity, the velocity right at that particular time. So instantaneous velocity really is it's a limit. Taking pre-calculus, or you have calculus, you will talk about limits. It's a limit as change in t gets arbitrarily small. And we are dividing by time, and you don't want time to be zero. But you can think of the change in position over the change in time. What would that equal if the time interval gets very, very small? What happens to position over time as the time interval gets very, very small? You can ask that question. And in calculus, you will take derivatives to do that. So the limit as change in t gets arbitrarily small will produce that instantaneous velocity. You make it on a calculator, you just can make it very, 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 very close to zero, very, very small. Smaller you can get it, the closer you're out to that instantaneous value. Now here's a crazy world line. There's a little time travel in this line. If you backtrack on this, you will travel through time. But take a moment to look at this. We'll talk more about this in class. I have a tangent line in here. So if I want to find the instantaneous velocity at that point, I could just find the slope of this tangent line. If I want the average velocity between these 2 points, I just find the slope of this line, but I miss the details of this motion. And you could continue on over here. Alpha here in this case is negative. And notice this curve right here kind of goes back this way in time. That's a weird time travel thing going on here. We'll talk more about what's going on with this in later lectures. But a position time graph can be used to find instantaneous velocity. You find the slope of that tangent line. The slope of the tangent line is called the instantaneous velocity at that instant. So instantaneous velocity, you evaluate the change in x over the change in t over shorter and shorter time intervals. You approach zero in the limit. But remember, you cannot divide by zero. That's not what I'm saying. So when v is constant, the instantaneous velocity will equal the average velocity. So constant velocity is also called uniform velocity. It's the same speed in the same direction. The instantaneous velocity, slope of the tangent line at a given time. It is a derivative of position with respect to time. When you jump into calculus, its value can be positive, negative, or zero. It is a limit. You would write the limit like this. V, instantaneous velocity, equals the limit of change in x over change in t as change in t approaches zero, as the time interval gets very, very small. If you haven't studied this yet, that's fine. We'll talk about it. We're going to do this graphically. This leads into taking derivatives, which you'll study in calculus. It's what a derivative looks like. You change the deltas to d's, and this would be the derivative of x with respect to t. The first derivative position with respect to time is the velocity, the instantaneous velocity in this case. So velocity is sign sensitive. You should look at that alpha angle. Now the question is there an instantaneous speed? Well, speed is not sign sensitive. Speed is the magnitude of the velocity. You can think of it that way, the magnitude of this instantaneous velocity. But you got to be careful with speed. It doesn't, the average doesn't always equal, as we saw in that example, the average speed did not equal the average velocity because displacement is different from distance. You have to be careful with questions like that. And we'll look at some examples of that. So average speed over a time interval change in t is the total distance traveled divided by the time interval. The average velocity over a time interval change in t is given by this equation. We could use the v bar again instead of v sub avg for average. We're going to be taking a lot of averages in this class, and that will be good enough for us. In fact, this displacement, or if you want to treat this as a distance in some cases, if you're just going one direction along a straight line, it will always equal your average velocity times the time. The trick is how do you calculate the average velocity? And there's a neat way of doing it if you're accelerating at a constant rate. If your acceleration is a non-zero constant. We don't want the acceleration to be zero. That would be no acceleration. We would want it to be a non-zero constant, like 9.81 meters per second squared, and it stays constant through time. Instantaneous velocity, it's a limit as change in t gets arbitrarily small. It's defined at each instant of time, may vary continuously with time. It's also the slope of a position versus time graph. You're looking for the slope of that tangent line. Instantaneous speed, the magnitude of the instantaneous velocity. The sign is plus or minus is irrelevant when you're talking about speed. You're not interested in the direction. You're not factoring that in. Now, acceleration tells how many meters per second the velocity changes in each second. This is a very interesting concept. We do have average acceleration. It's the change in velocity over the change in time. You could write it all out as v minus v naught divided by t minus t naught. It is sign sensitive. It is a vector quantity. It has magnitude and direction. Typically, something will break if the acceleration becomes too high. And, if you have a very, very small impact time, like in a collision, like dropping an egg on a hard surface versus a pillow, if that impact time is small, it actually will produce great forces, and you have great accelerations, which cause things to break. You really want to increase that impact time to reduce the forces on something, such as an egg, to reduce the accelerations. In fact, human beings can only withstand so much acceleration. It does limit us in terms of space travel and airplanes and that sort of thing. We have to design our vehicles so that we can survive the great accelerations. It's possible for you to go unconscious at about 7 Gs is what it's called. G being the acceleration due to gravity. We'll talk more about that later, but there are some limits on the human being in terms of accelerations. We only can withstand so much before it becomes very, very risky. So here's a question. A tennis ball is bounced on a hard surface. Its incoming velocity is 5 meters per second downward, and its outgoing velocity is 5 meters per second upward. The estimated impact time is 0.01 seconds. What is the average acceleration of this simple collision? I would like you to do this and bring your answer into class. Thank you. Instantaneous acceleration. How fast does the velocity change? We want to evaluate this change in v over change in t over again, shorter time intervals approaching zero in the limit. When a is constant, instantaneous acceleration will equal the average acceleration. Now, when we're graphing velocity versus time, and we find the slope of the tangent line, we are finding this instantaneous acceleration. So it's a first derivative of velocity with respect to time. It's also the second derivative of position with respect to time, if you're interested in jumping ahead and looking at some of the calculus. So here's the limit. Imagine a graph of velocity versus time. If you find the tangent line at any particular moment, and you will be finding the instantaneous acceleration. So it's the limit as change in v. It's a limit of change in v over change in t as the time interval approaches zero. You could write it as a derivative. This first one is the derivative of velocity versus time. This is the second derivative of position with respect to time. This is you don't need to know this, but you should be familiar with this limit notation, and that to find this, we find it graphically on a velocity versus time graph. So here's a question. Does an object with a negative acceleration always slow down? I should know in physics, we typically we don't use the phrase deceleration. We use the phrase negative acceleration. We have positive acceleration and negative acceleration. So I'd like you to answer this question as well. So acceleration, the rate of change of velocity. There's the formula, change of velocity. You could write it as v2 minus v1, or you could write it as v minus v naught. So any change in velocity implies an acceleration. So here are three things to look for. If the speed is increasing, like your gas pedal, use it to increase your speed in a car, you are accelerating. If the speed decreases, like using the brake pedal, you are accelerating. I know that sounds weird. If you change direction by using your steering wheel, you are accelerating. So increasing, decreasing speed, either one, increasing speed, decreasing speed, or changing direction. If you notice any of those things in the motion of an object, that object is accelerating. So going in a circle at constant speed, even though you're going at constant speed, because you're also constantly changing direction, you are accelerating. So instantaneous acceleration, you take the limit of and it's just making it as small as possible for change in v over change in t. Make it small as possible, that average expression, that slope, and you will get the instantaneous acceleration. It's just the slope of the tangent line. You have to have a velocity versus time graph. So the units of acceleration, once again, are meters per second or meters per second squared. You also could use miles per hour per second. That's a common one. We'll talk about the acceleration due to gravity as in both of these units. We'll use 9.81 meters per second squared. We'll also use 22 miles per hour per second as a nice value. We'll also use 32.2 feet per second squared. So if you notice, there's always that dimension of length over the dimension of time squared, and that's something different. Okay, we can calculate only average accelerations from the net change in velocity and time elapsed. In physics, we almost never talk about deceleration. As I said earlier, we could talk about negative acceleration. All right, once again, velocity, rate of change of position. Acceleration, rate of change of velocity. Values of position, velocity, acceleration aren't directly related. All may change continually with time. Here are some graphs of position versus time where the acceleration is not constant, it's varying. You can see this graph down here, acceleration versus time. It started up here in the positive value, went through 0 and down in the negative value. This will affect the position time graph and also the velocity time graph. And these little lines here, you're trying to find the slopes. The slopes have meaning. We'll talk about that. You also could have motion under constant acceleration. If you look at the acceleration versus time graph here, these are just rough graphs. The acceleration is some positive value. That produces a straight line for the velocity time graph. That means the acceleration is constant, has a constant slope. That's why you have a horizontal line here. And also, it will create a quadratic function for position. This isn't quite right the way it's drawn here, but we will talk about this. So you get a parabola for your world line, constant slope for the velocity versus time graph. So we'd say, the acceleration is uniform or constant. We don't mean zero as a constant. I know zero is a constant, but we mean a non-zero constant when we're talking about constant acceleration. Or it's better to say uniform acceleration. So when the acceleration is uniform, as you see, I wrote here constant, but it's understood what it means. Non-zero constant. The instantaneous acceleration will equal the average acceleration. And this is the type of motion we're going to approach in Chapter 2, motion under uniform or constant acceleration. There are often several ways to solve motion problems involving constant acceleration, some easier than others. The position varies with the square of the time for constant acceleration. And for constant acceleration, the velocity changes linearly with time, but non-linearly with distance. And that's it. Thank you.